because the losses on the resistor is very high, so it will generate high temperature. So so this mask is rarely used. Okay, let's say another mask. We can change the voltage. Just change the terminal voltage. Change the terminal voltage. The characteristic curve is you see big A. There are several straight line that to different voltages. Every voltage has a straight line. And first, the distribution working at point A and point A. That's the same at first working at point A. And this time we decrease the terminal voltage. Decrease the terminal voltage. So the distribution will work on another curve. So it will turn from the status will turn from A to B, and to progress from A to B, the speed will decrease. The speed will decrease. This figure is just similar to the Form 1. The speed will decrease, and then speed decrease, EMF decrease, EMF decrease. So the armature increase. So the armature increase. The armature current increase. So the torque increase. The torque increase. So it will go to another balance point. So it's C. It will go to C point. And this point is a balance. It's a balancing status. The speed will be constant to this point. N2. N2. So from N1 down, decrease to N2. And this is the second method to change the voltage. And the third one, we can change the flux. We can change the flux. Also, we see the characteristic curve here. It's different from the former two cases. How to change the flux? Just insert a voltage resistor current, adjustable resistor in the field circuit. So first point is also A. It works in initial. It works at A point. The speed is N1. N1. The speed is N1. So when you adjust the flux, we insert a resistance to it, so the flux will decrease. The flux decrease, and then if the flux decrease, so the EMF will decrease. EMF decrease here. EMF decrease. current will increase. So yeah, so the current will increase suddenly. Increase very fast. The increase suddenly increase. Lead to the torque. The torque will increase also. The torque will increase also. Yeah. So the speed of the motor will increase until to the new balance status. The new balance status. So it will from A to B to C. Yeah. So the speed increase to the N2. Yeah. So it's also the progress is from A to B to C. It's just the details. So it's the third method. Let's see. We know the armature current. The armature current is proportional to the machine power. So the circuit will lead to losses in the armature conducts. It will generate high temperature. The heating of the armature conductors can be too high.
Yeah.
So we have to limit the heating of the conductors. So how to limit it? We know the power is the product of voltage and current. So we just limit the power. So every motor has a rated power. Yeah, every motor has a rated power. However, the speed increase, we have a limit. We have a limited power here. So it will limit the heating. So to protect the motors. So if a motor is operating and its rated terminal voltage, and rated power and rated field current, so it will be running at rated speed. So this is the power limit for DC motor. Okay, let's see next aspect, starting and braking of DC motor. If we apply full voltage to a stationary separate DC motor, the initial current in the armature will be very high. It will cause some risks. And maybe the armature will burning out, or will damage the commutator because large current will generate heavy sparks. So it will destroy the commutator, and also the wire. The wire will be overloading. So the wire may be destroyed. The shaft may be destroyed because the mechanical shock. So it's suddenly a big torque to the mechanical shaft.
And also bearings,
Yeah.
sometimes it's broken.
Or damaging the driver equipment, just the source, the DC source. The current may be too large, so it will destroy the source. So we should not give full voltage to a DC machine at the beginning. And here is just for the separately excited DC motor or shunt DC motor. But if it is a series DC motor, so it's no problem. So what's the solution to start a shunt DC motor or like a separately excited DC motor?
Is that from a small voltage?
So we have two starting methods. Yeah.
One is connect resistance.
Yeah. Resistor. Insert a resistor here. RST. Insert a resistor in series with armature circuit. So when you start the KM, the switch KM is turned off. So it will limit the current in the armature circuit.
Yes.
It will limit the current. But when the speed go to speed is big enough, large enough, we'll turn on the KM. Turn on the KM. And second method,
Reduce the voltage.
we to give a lower voltage.
I use this one for reset my motor.
To a lower voltage, but the voltage will be adjustable. So we need a special adjustable voltage power supply. But this kind of power supply is generally too expensive.
Yes,
Too expensive.
My motor is 24 volts. So firstly I give from 5, 10, 12. This is my adapter. After that, when I have enough speed, I just give 24 volts.
Yeah.
Not suddenly 24 volts. If I give this one, I lost my
Just
3 volts.
voltage. And another aspect is how to break a DC motor. Yeah. A DC motor usually with heavy load. If it have heavy load, so just the mechanical friction can stop it. It's hard to do it. So we usually have electromechanical brake. Yeah. What are into dynamic braking or
Plugging.
plugging. Yeah. Or plugging. So we see the dynamic braking. The principle can be seen from the figure A to B to C. First, the DC motor was working. This time, the switch is on left. But if we want to break the motor, so we just turn the switch from left to right. Yeah. From left to right. So when the switch is turned right, so the armature is connected to the resistor. This resistor. The armature current will be inverse to the former one. Yes, the current is the direction of current changed. So the direction of torque changed too. Yeah. So there's a reverse torque. There's reverse torque to stop the DC machine. To stop the DC machine. The reverse torque will bring the machine to stop very fast, rapid and smooth method to make it stop. Yeah, this is the terminal characteristic curve. Yeah. So the blue line is the characteristic curve. It's just use the equation. The speed is proportional to the resistor. Resistor RBK. Resistor we inserted is just proportional to the resistor. So if we give a small resistance, RBK, the speed will faster into 0. But this time it will generate a large current. So we should limit the resistance of this resistor to avoid the danger. And the plugging method is we say the figure A to A to B. It's just a reverse the terminal of the source. You see here, the plus one. Yeah. The plus. This is plus. When we switch the switch from left to right, the plus one is to here. So it and a reverse voltage on the motor, reverse voltage on the motor. So it will generate reverse torque to stop the DC machine. So this is a torque speed curve. Torque speed curve is I'm showing in this figure. The blue straight. So the slope is a little big than the bottom one. It's according to the equation here. The speed also proportional to the resistance. Okay. Compare the plugging and dynamic braking with the same initial braking current. Plugging is faster than the dynamic method. But the dynamic method is a simple method. It's a simple method. So we usually use the dynamic braking method. It's much more popular. So they are all for the electromagnetic DC machines. Here we will present the permanent magnetic DC machines. What is a permanent magnetic DC machine? So just the poles are made of permanent magnets. So we don't need the additional power supply, for excitation. But the principle of PMDM is similar to the ordinary DC motors, except that the permanent magnet poles are used instead of the current excited magnet poles. So in the past, permanent magnets were only used in motors with small input, just like a toy motor. It's so small, just big than a coin. It was very small, so a lower power. It has weak magnetic force.
This is only 3 volt 3 volt motor.
And it's easy to the magnetization. So they are mostly used in toys or teaching instruments, and low power one.
3 volt only, sir. This is 3 volt.
So let's see the construction of a small toy DC machine. So the battery is nylon can. Nylon can. So we give a reverse voltage, and we have an opposite direction. This is the characteristic of the DC motor. They can inside the machine.
The 2
brushes. So it's simple brushes. Maybe a bronze. So it also it's used with the commutator. We use with the commutator to change the direction of current. So this is armature. This armature has 3 poles.
120 degree 3 poles.
Has 3 poles. This kind. So 3 poles corresponding to 3 bars, and the commutator has 3 bars. We also see inside the machine there are permanent magnet. Permanent magnet. So it's just a 2 pole. This is for just so the permanent magnet DC machine is simple DC machine. Simple DC machine. So let's say the industrial gear motor.
Gear motor.
In the past about 10 years, the development of permanent magnet material, such as rare earth. So it fast developed. So the DC motors moved from toys instruments to other large motors. For example, to vehicles. So it can make big high power DC motor with permanent magnets. Yeah. It's like this one is for industrial motor. It will generate strong magnetic force. So let's see the advantages of the permanent magnet DC machines. First, it do not need a field circuit. It's just use the magnets. So no circuit losses.
Copper loss?
Yeah. So no field windings. It's smaller than shunt DC motor. So let's see the disadvantages. Low flux density. Generally to the decimers like toys, but not. Some extent it's solved. We use the rare earth material. So it's so the low flux density is not a disadvantage now. But it still has the risk of demagnetization. It still has this risk because high temperature or violent vibration, it will all cause the demagnetization. And the third one is not easy to control the speed by varying the field current because it's constant. The flux is constant, so it's not easy. Not possible. It's not possible. It's not easy. We can also control the flux by some other methods.
In Changsha Metro, this metro rail, they use this DC or AC.
What?
Changsha Metro rail, this metro, they use AC motor or DC motor?
What application?
Subway, metro rail.
Subway?
Yeah.
Subway. The train.
Yeah, the train.
The train. I know it's called DC.
It's three phase or single phase.
Also can use.
But
usually DC.
This is three phase or single phase. There is three phase or single phase.
Single phase.
Single phase.
It's a high voltage.
High voltage. It's a atomic loss. So AC tower down.
So this is a characteristic. Also the magnetization curve. Magnetization curve. Yeah. The pH curve. So the flux can be brought to zero. If they are opposite So it still has it can change the polarity of the magnet. So this is the curve, and this also are different residual flux. So we just see it. Okay, let's see the principle of DC machine. So it just here the stator, the magnet, or the armature, not the commutator, the brushes. the field and the field is fixed. The field is fixed by permanent magnet. Yeah, so the fix is constant. And also there's a force. The force according to Fleming left-hand rule. Yeah, so we can just the force. The force let the armature to rotate. That is the principle. The principle we see as LSFIF. So it's constant. It's constant. Yeah. Just it determined by the magnet strength, by the number of turns. Yeah. So it's constant. Cannot be adjusted. And this is the cross section. Yeah, we see the gradient of the permanent. Is the direction of the magnet. It's the rotor. So and also the magnet equivalent circuit. There's some simple calculation examples on the textbook. We can do the calculation. We see the EMF. How to calculate EMF for ordinary DC motors is according to this equation, but for permanent magnet is according to this equation. The EM is equal to Ka and phi d. Yeah, it's the product of Ka and phi d. It's just the EM. So it's a new equation, and the equivalent circuit is just like this. So we can calculate the EM easily. Just we should know the Km. Okay, that's our summary. We have present all the DC motors. Yeah. We know DC motor or DC generator generally have a commutator and brushes, and the disadvantage is the construction is complexity, and it's expensive to AC motors. But DC motor still have many important applications. Not only for low power applications, but high power application we also have DC permanent motor. Okay, that's all for the DC machines. Yeah. After the vacation, we will have AC machines, chapter 6. Chapter 6. So we can preview the chapter 6.